What's up, everybody? My name is Demetri Kofinas, and you're listening to Hidden Forces, a podcast that helps investors, entrepreneurs, and everyday citizens get an edge by equipping themselves with the knowledge needed to anticipate the challenges and opportunities of tomorrow. By sharing my critical thinking approach and by challenging consensus narratives about the power structures shaping our world, I help you make the connections to see the bigger picture, empowering you to make smarter decisions. On this week's episode, I speak with Steven Koonin, director of NYU's Center for Urban Science and Progress, who also served as Undersecretary of Science at the U.S. Department of Energy under Barack Obama, and as chief scientist at BP, where he was a strong advocate for research into renewable energies and alternative fuel sources. The subject of climate change, or more specifically, the science of climate change, has become, like almost everything else in our society, a matter of political identity. A recent Pew Research study found that Democrats are more than 3 times as likely as Republicans to say that dealing with climate change should be a top priority. And yet, if you ask people, independent of party affiliation, for their views on climate change and why they believe what they believe, most of them will struggle to give you a coherent answer. In fact, very few people, and this goes for politicians, journalists, and even academics, have actually read the reports put out by organizations like the IPCC and others responsible for doing the actual research that we all cite when we talk about, quote, the science. And I am as guilty on this as anyone. After all, why would I want to spend a minute of my time learning about exactly why we are so screwed, about how exactly we've destroyed the planet and, quote, broken the climate? I've read all the headlines: climate catastrophe, climate disaster, the earth is burning. But how true is that exactly? Are we really facing a climate apocalypse? Is climate science really, quote, more reliable than physics? Something that journalist David Wallace Wells said in a recent appearance on the Joe Rogan podcast? Not according to my guest, but more importantly, as he would say, not according to the science, which, to borrow from the book's title, is very much unsettled. Now, before you react to that very provocative headline, no one is saying that climate change is a hoax or that anthropogenic warming isn't real. The purpose of this conversation is not to surreptitiously undermine the consensus view, nor to troll those who believe strongly in it. Rather, it is simply meant to inform and educate me and those of you like me who either haven't read the reports or are simply skeptical about just how bad the situation is and what's required from us in order to solve it. For the record, this is a subject that concerns me deeply, but the doom and gloom narrative surrounding it, I think, is actually counterproductive to helping us actually address the problem. This is a very complicated subject, and we spend the next 2 hours between the first half and the overtime working our way through the data, what it says, and what the models predict about not only future warming, but also the incidence of droughts, forest fires, hurricanes, rising sea levels, climate-induced migration, and pandemics driven by a warming planet. In the subscriber overtime, we focus most of our attention on the incentives that account for these widely divergent narratives on climate, the importance of morals and values in thinking about how we structure climate policy, and the missing components of costs and trade-offs that we need to think about when coming to decisions on how best to adapt our societies and ourselves to the changing climate. We also discuss geoengineering, including carbon extraction and the use of aerosols to dampen the sun's rays, as well as alternative sources of energy like wind, solar, and nuclear, and their respective roles as alternatives to fossil fuels in the coming decades. And with that, please enjoy this timely and informative conversation with my guest, Steven Koonin. Dr. Steven Koonin, welcome to Hidden Forces.
Happy to be here. Happy to be talking. Thank you.
My pleasure to have you on. So can you give me and my listeners a sense of your background, how you became interested in this field of climate science, and what roles you've held in both the private and public sector.
Yeah, so let's see, a brief bio. I grew up in New York City, was educated in New York City public schools, particularly Stuyvesant High School, which is a special high school for science and math. That was about 50 years ago, and I had a wonderful education there. Went off to Caltech for undergraduate work, bachelor's in physics. I went to California because it was the late 60s and it was the thing to do. PhD at MIT in theoretical physics, then back to Caltech as a professor starting in 1975 for just about 30 years. The last 9 of those years, I was the provost at Caltech as well, with responsible for the research and education programs across the institute. In 2005, I went to become the chief scientist for the oil company BP. It was a big transition, but taught me about the private sector. I knew energy would be important, and I went there to help them figure out what beyond petroleum really meant. I did that for 5 years, based in London, and then returned to the U.S. when my friend Steve Chu became Secretary of Energy. He asked me to come help out, and I became the Undersecretary for Science in the Department of Energy during the first Obama administration. After 2.5 years, which is about the average time in government, I left the government and came to NYU to start a center about big data for big cities. Did that for 6 years, and now I'm just a professor at NYU teaching energy and climate science at the graduate level. You know, there was a famous physicist, Leo Szilard, who was most famous in the early 20th century for having written the letter that Einstein sent to Roosevelt to start the Manhattan Project. And Szilard was quite a character. He had his own 10 commandments, and one of them is you should reinvent yourself every 6 years. And I've sort of taken that to heart over the last couple decades of my life.
I totally feel that. So what was your role as Undersecretary of Science in the Obama administration? What were you tasked with?
Well, I was fortunate not to have to deal with the nitty-gritty of budgets and such. And so I was, at one level, a strategist for the department. I wrote the first technology plan for the government in energy technologies. What technology should the government be investing in? How should it think about its investments? And so on. And in another way, I was the scientific conscience for the department. Many people say I was Steve Chu's Steve Chu. Steve is certainly a fine scientist, but he needed somebody to push back against him sometimes scientifically, and that was another one of my roles. So, I mean, if I look at where I'm coming from, I'm a physicist. I love understanding how the world works, and I've applied that to many different areas of science. I'm an educator. My greatest joy is seeing faces light up when I teach somebody something, and been doing that in the classroom now again for a couple years after a hiatus of about 20 years. And maybe most importantly for the present discussion, I've got experience as an advisor on science and technology to decision makers. In previous decades, I've weighed in on the Human Genome Project for the government, on various weapon systems, on radiological terrorism. I testified to Joe Biden in the early 2000s on dirty bombs when he was running the Foreign Relations Committee. And I've had a long involvement in the stewardship of the nuclear weapons stockpile that this country has. And then in the private sector, I was again advising the chief executive of BP. I still advise numerous energy companies. So all of those come together now in the particular take on climate science that I'm trying to educate the public about.
So tell me a little bit more about that. How does that all come together? And what led you to both become interested in this field and then ultimately to write a book with such a subtle, I'll admit, but nonetheless controversial title, given the view among many scientists and members of the media that the science is, quote, settled when it comes to anthropogenic climate change?
Yeah. So, of course, I've been interested in the subject for a long time. I even started an observational program in the early 90s to try to measure one aspect of the climate. But for The time I was in BP and then in the government, the focus was on the technologies that we might be able to develop and deploy in order to, forestall the worst of climate change. And I really had not dug deeply into the science. But starting in late 2013, 2014, I was asked by the American Physical Society, which is the professional society representing 50,000 physicists both in the US and worldwide, to have a look at the statement that they had put out on climate change. They had put one out in, I think, 2007 and 2008, and it was rather controversial at the time because it said the evidence was incontrovertible, we've got to act now, et cetera, et cetera. And incontrovertible really gets a physicist's attention because it means, we understand this absolutely. And many people at the time, although I was not one, because I was busy with other things, took issue with that. And so they, in fact, had to reissue an explanatory text for the statement in about 2009. Anyway, 2013 comes along, and I get asked to chair a committee to reissue, update the statement. And I decided rather than simply endorse what you have cited as the consensus, we were, after all, physicists, and we were going to dig deeply into the issue. And so I convened a workshop in January of 2014. 3 consensus scientists, many of them IPCC authors, and 3 people who took issue with that consensus, and then a number of others of us who were on the committee to consider the statement. And we talked for a day. There were presentations and discussion. There's a transcript up on the web that one can find. And I came away from that meeting really shaken, unsettled, to use the book's title, if you like, that the science was nowhere near as solid as what had been portrayed in the media, or certainly what the politicians were talking about. And so I wrote an op-ed for the Wall Street Journal in September of 2014, in which I laid out some of the concerns and issues I had understood. A lot of response, over 2,000 online comments to that article in the journal, many of them supportive, but some saying, of course, you idiot, you don't understand, et cetera, et cetera. And so I started paying close attention, not only to the science, but the way it was being portrayed in the media and the politicians, their discussion of it. And the way I like to summarize the statement is, I'd like to adapt a line from the movie The Princess Bride. And one of the characters keeps using the word inconceivable. And at some point, Inigo Montoya, who is the principal character in the movie, says, "You keep using that word. I do not think it means what you think it means." And I think the adaptation to the current situation is, I don't think the science says what you think it says. Everybody quotes the science. The President Biden, who is a fine leader, he keeps saying, it's the policy of my administration to listen to the science. And then you've got John Kerry, who said, there's no doubt in anybody's mind that the science is absolutely certain. And so you have various people like Bernie Sanders, Mark Carney, the former head of the Bank of England, Bill Gates, my good friend Ernie Moniz, who was Secretary of Energy in the second Obama administration. They're all talking words: existential threat, climate crisis, climate emergency, climate disaster. And in fact, when you actually read the literature and the reports, there is no support for that kind of hysteria at all. And so I think people really want to understand, should be understanding, what does the science really say? And that's why I've written the book, to highlight some of the things that are in the popular perception that just ain't so.
So what does the science say? And perhaps just as importantly, what do we mean when we say, or when we talk about the science?
I think in the popular discussion, the science is what is presented in the assessment reports. So these are reports that are issued periodically by the United Nations Intergovernmental Panel on Climate Change and the U.S. government every 4 years in the National Climate Assessment. And these reports are meant to survey, summarize, and make concise or understandable for non-experts exactly what we know and what we don't know about the science. And the problem is that there is a long game of telephone that goes on, which starts with the peer-reviewed literature, the reports of the basic research written by scientists, for scientists, peer-reviewed. There is then the process of putting the assessment reports together, which can go on for a couple years, typically involve hundreds, if not thousands, of people contributing. They are a narrative, if you like, that are meant to convey things to non-experts. Then there are the summaries for policymakers of the assessment reports, which further distill the understanding down. And then finally you get to the media, which translate it for the general public. And, very few people actually read the assessment reports. And so there's ample opportunity for mischief along that chain of refining and filtering to spin things one way or the other. And in fact, if you look at certainly the media and the summaries for policymakers, there are a lot of things they don't tell you, or there are things that they misrepresent when you actually go read the assessment reports or even the underlying literature. And so that's what people mean by the science. And, my guess is that, I don't know for sure, but certainly Bernie Sanders, John Kerry, maybe even Bill Gates, I don't know, have not actually read the reports, let alone the underlying literature.
So that's actually a good segue, because I wanted to spend some time getting really clear on what it is that we do know, and also to clearly differentiate between what the reports themselves say, in other words, what the data says, and the assumptions that are baked into that data, and the wide variety of projections, because there are so many different types of projections based on different types of models, and these models diverge dramatically in some cases. I think people would be surprised to learn just how much they diverge. So I'd love to get into that.
Okay, let's try to separate the conversation into what we've observed about the climate over the last century and a half, and even further back through proxies, the models themselves, and then the projections going forward. So let me tell you some things that are in the report that might come as a surprise to many people who've only gotten their information from the media. And, these are direct quotes from the most recent UN report. We have low confidence regarding the sign of the trend in magnitude or frequency of floods on a global scale. We have low confidence in any global scale trend in droughts or dryness since the middle of the 20th century. We have low confidence in trends in small-scale severe weather phenomena like hail or thunderstorms. And we have low confidence in large-scale changes in the intensity of mid-latitude storms since 1900. And then you dig a little bit deeper into some of the other phenomena. U.S. heat waves are now no more common than they were at the beginning of the 20th century, and the warmest temperatures in the U.S. have not gone up in the past 50 years. Global wildfires have declined more than 25% since 2003, and the last year, 2020, was one of the least active years in the wildfire record. There's no detectable human impact on hurricanes over the past century. And the one that is in many ways a bottom line is that the net economic impact of warming of 3 degrees, which is twice the Paris goal, if it happened, would be minimal. And all of these statements are not Steve talking, but they are in fact exactly what's in the assessment reports or the recent quality peer-reviewed literature. So, the statement that we've already broken the climate is just not supported by the data.
So maybe it would be best if we tried to separate some things out here by order of importance. Let's focus on temperature for a moment, because I think that's the metric that's most top of mind for most people and most directly related to warming. What have we seen in terms of rising temperatures on the planet over not just the course of the last 100 or 200 years, but going as far back as we have records? And what do we know about the effects that warming had on the planet?
Right. So, first of all, when we talk about temperature, the temperature is different everywhere and every time. And so we generally talk about a global average temperature. And we talk about the anomaly in that average temperature, namely, how much does it differ from expectations? And what we've seen since about 1900 or 1880, the time when we started to have good global records of temperature, of course they get better as the decades go on from 1880, is that the global average temperature of the Earth has risen by about a degree centigrade, which is 1.8 degrees Fahrenheit for U.S. listeners. But that rise has not been steady. It rose pretty rapidly from 1910 to 1940, actually went down from 1940 to 1970, 75, and then started going up again, but in the last decade or so has been relatively flat. I mean, still increasing, but relatively flat. So we've seen a warming not steady of about a degree over the last century, last 120 years. Before that, if you go back to the 1600s, we had what was called the Little Ice Age. And while there's some controversy about whether that was a global phenomenon still or not, I think most people, almost everybody, and certainly the assessment reports say it was about half a degree to a degree cooler than it was at the beginning of this century. The beginning of the 20th century. And then if you go back even further, there are periods in the past over the last many thousand years since the end of the Little Ice Age where it was, in fact, we think, as warm as it is today. So variations in the temperature are not at all unusual. What is really the issue for us is whether the recent warming that we've seen over the last century, to what extent is that driven by human activities, or is it part of the natural variation of the system? You can go back further. There are the glaciations, the ice ages popularly. If you go back to the last time we were not in a glaciation, the so-called Eemian period, about 125,000 years ago, the temperature was 2 degrees warmer, we think, and sea level was up to 6 meters higher, 20 feet higher than it is today. And so variations in the climate are not at all unusual. The real question, as I said, is to what extent are the recent changes influenced by humans?
So let's look at just 1940 to 1970, where temperatures actually dropped. Because I think that raises some interesting questions, because clearly the world was already industrialized. We weren't generating as many hydrocarbons and releasing molecules into the atmosphere at the rate that we have been after, let's say, 1980. But certainly it wasn't an insignificant contribution. How do scientists explain that?
They don't. If you look at the official assessment reports, not Steve talking, they will say it's some combination of natural variability, and we should talk a little more about natural variability in a moment, human influences, and bad data. And that's why we have no explanation of that. So my own sense is that there is demonstrable long-term variability in the system. We see cycles over 60 years, 70 years, and unless you understand those cycles, they can pollute or contaminate your understanding of what's going on.
So is that another way of saying that there is a lot of noise in the channel and that we're trying to focus in on this one signal of human contribution to climate change, and we're trying to draw a direct causal connection between the warming that we've been observing over the last 40 to 50 years in particular and human activity? And then on top of that, there seems to be a strong view that if we can get our act together, so to speak, as a global community and make significant changes to how we operate at scale, that we can effectively reverse the warming that's expected. Do I have that right? I mean, how did that view come about?
So I think the first thing we need to understand is that humans exert both a warming and a cooling influence on the planet. The warming influence we exert is through the greenhouse gases, largely, that we put into the atmosphere, most of that CO2 from the use of fossil fuels. We exert a cooling influence by the aerosols, the particles that we put into the lower atmosphere by burning dirty coal, for example, putting sulfur up into the atmosphere. And those two play against one another. And the net human influence is the difference between the two, about comparable to the CO2 influence net. The other thing to understand is that those human influences are physically small. They are about 1% of the natural energy flows in the system. So we've got this big system and we are tickling it a little bit. We're tickling it in a constant way. We're always adding net warming influence, but nevertheless, it's very small at the level of 1%. The third thing to understand is that there's a lot of noise in the channel, natural variability, on all scales, from year to year, from decade to decade, from century to century. And then finally, you have to understand that we have good observations with a precision comparable to what we need to understand the response to human influences. We only have that for about 120 or 130 years. And even then, it's not great. The oceans are one of the most important parts of the climate system. And of course, they're very difficult to observe. And we don't have really good ocean data, except for the last 20 or 30 years.
On ocean temperatures, is that what you mean?
Temperature, salinity, currents, those are the things that are important in the ocean. And so, the consensus does as good a job as they think they can, and they would say that at least half of the warming since 1950 is due to human influences. But, could it be, as I look at it, could it be a third or a quarter? Yeah, it could be.
Well, when you say it could be, here's where I want to pull out, because what often times occurs in these conversations is because the consensus view is so strong, when they hear someone say could be, what they're really hearing is this person's just throwing shade. They're just basically saying, oh, yeah, it could be. Anything could be. I could be made of silicone. But when you say could be, what are we talking about here in terms of likelihoods?
Yeah, so, of course, all of these statements are probability statements, and there's no firm number. We can at best give a range, saying there is a 10 to 90% chance that the number is in this interval. But those things have shifted around a lot as we understand more, as the models get better, and as our understanding improves. So, could we see warming as much as 4 degrees? Yes, but we could also see warming as little as 1.5 degrees. And uncertainty is an intrinsic, perhaps the central part of science. The general public doesn't understand that, then the politicians want certainty. So there is this kind of clash of cultures between the probabilistic thinking of scientists and the need for certainty that people naturally have.
Well, so a couple thoughts. I think this is a good opportunity to get into the modeling, but I also want to say that I think part of the reason why these conversations become so emotional for people and seem so morally clear-cut is because we're presented with projections of what we think will happen if we don't act, expressed as near certainties, while at the same time the costs of action are either deemed to be incalculable or they're ignored entirely. And I absolutely agree that our discomfort with uncertainty is a big driver here, and it is, I would argue, impairing our decision-making, regardless of what the proper course of action is, exactly because we're assigning incomplete values to the things that we're discussing. So to that point, I'd like to focus in on the uncertainty and have you explain to me and to my audience how the Earth warms, how that process works. Because it's a complex process that begins with the sun. It also involves the molecular constituency of greenhouse gases in the atmosphere, as well as the Earth's reflectivity. And then let's get into how the models are developed.
So let's talk a little bit of science about the temperature of the Earth. And the temperature of the Earth at the surface is set by a balance between the warming influence of the sunlight that gets absorbed by the Earth and the heat radiated by the Earth. After all, if it's absorbing the sunlight, it's got to get rid of the energy somehow, and it does that by radiating heat. On the sunlight side, the warming influence, about 30% of the sunlight is reflected by the Earth, by the land, the oceans, importantly the clouds and the snow and ice toward the polar regions. And the balance of that sunlight, 70%, is absorbed by the planet and what goes to drive the weather systems, the currents in the ocean, and so on. In order to balance that warming, the cooling influence is the heat radiated by the Earth. And the basic physics of that heat radiation, namely infrared radiation, was well understood. It was established by some physicists, Stefan and Boltzmann, in the 19th century. And it's understood that as the temperature of the Earth goes up, it radiates more. And so it is a natural thermostat, if you like, that sets the temperature of the planet. If there's more sunlight absorbed, then the temperature will go up, there will be more heat absorbed. And if you go through that balance quantitatively, as you do in any simple climate class, you discover that the average temperature of the Earth is 255 Kelvin. If I could translate that into ordinary human temperature scales, it's about minus 20 degrees centigrade. And that's much colder than what we observe. It's actually about 15 degrees centigrade positive that we see in the Earth.
That's what the temperature would be if there were no atmosphere.
Atmosphere, that's correct. And what is keeping the temperature at its observed value of about 15 degrees centigrade is in fact the so-called greenhouse effect. And that is some molecules in the atmosphere, particularly water, but also CO2 and some other less common molecules, intercept the heat that's radiated from the ground and slow its progress out to space, and therefore make the planet warmer than it would be. It's like, the insulation provided by a jacket or a blanket, which impedes the flow of your body heat and hence keeps you warmer. And what humans are doing is adding carbon dioxide and other gases to the atmosphere that are increasing the effectiveness of this insulation, and so slowing the progress of heat back out into space and therefore warming the surface of the planet. We should realize that the warming is not uniform over the globe. It's warming much more rapidly in the polar regions, in particular the North Pole or the Arctic. It's also warming more rapidly on the land than it is over the oceans. And as we mentioned, the average warming has not been steady at all, but has gone up and gone down a bit over the last century and a half.
So is that what accounts for the more rapid warming at the poles and on land versus the ocean? Do we understand that?
The land has a smaller heat capacity. It responds more rapidly to warming influences. The oceans take a longer time to warm. And in the poles, we're seeing a lot of it is what's called the ice albedo feedback, where in fact, that as the ice becomes less common, the reflectivity goes down, and so the poles warm a bit more rapidly than the equator.
Now, because the ice sheet reflects more sun, and as the ice sheet dissipates,
correct,
the oceans begin to take in much of that warming.
Correct.
So let's get into the modeling now, how the modeling is actually done, because this was actually, for me, one of the more fascinating parts of the book. I had no clue how, to any significant extent, how climate models are actually developed, what they look like, and most importantly, the extent of the subgrid assumptions that are made. So what goes into that?
The popular perception is, heck, it's just physics, right? And we understand physics very well, and so we should be able to do a wonderful job of modeling. In fact, it's not at all like that. It is an enormous challenge to model the climate on the scales that are useful for understanding how it responds to human influences. The way in which it's done is to cut the Earth, both the atmosphere and the oceans, into small bits, voxels, volume elements, like pixels, but 3 dimensions. And there are hundreds of millions of these that you need to cover the Earth. You then use the basic laws of physics to move the energy, the atmosphere, the momentum, the matter through these voxels, time step by time step, as small as 10 minutes sometimes. and watch the climate evolve under solar heating, greenhouse gases, infrared radiation, and so on. And we build these physical processes in. There are, however, a number of practical problems that make it very difficult to do this in a useful way. Because computer power is not infinite, we have a significant computer power these days, but nowhere near enough to do the job, right? You can't make the boxes too small, otherwise you get too many of them for the computer to handle. Remember, we've got to step these through 10 minutes at a time over centuries. So that's an enormous, let's say, a billion time steps or something.
So the
like
computational impact of that is exponential.
Is enormous. And the runs of the modern models take months to run on the fastest supercomputers. So we can't make the boxes too small, otherwise we get too many of them and we can't compute. But there are many processes in the climate system that happen on distances smaller than the typical 60 miles of a box. Clouds are the most important one. And clouds are a couple miles across. I'm looking out my window here in the Hudson Valley at the moment, and they're probably, half a mile, quarter mile across. And of course, they're varied across the sky. And because you can't describe those explicitly in the computer, you have to make assumptions about what the clouds are doing in the boxes. And depending upon the kind of assumptions you make, you'll get different answers. So that's one of the major sources of uncertainty.
Let's just talk about that example. What are those assumptions based on? And in the case of clouds, how significant and important are clouds in contributing to warming or cooling?
Yeah. So the clouds can warm or cool. In general, high clouds warm because they're a little more effective in trapping heat than the atmosphere around them. Low clouds in generally cool because they reflect more of the sunlight and don't have so much influence on the heat interception. The assumptions that need to go in, so you've got this box, actually you've got a whole stack of boxes up in the atmosphere over a particular part of the ocean or the land. The box is 60 miles on a side, but in general is very thin. The boxes need to be thin in order to describe the atmosphere, which is really a thin layer on top of the planet. So I've got these basically layers in which I've got to make assumptions. How many clouds are there? Given the temperature and humidity in the box and other things in the surrounding boxes, how many clouds are there? And what are their properties? How much light do they let through? And people try to make those assumptions based upon basic physical understanding, observations. We have some spots on the globe where we try in detail to observe the clouds, and laboratory experiments of how clouds are formed.
So basically sample size the clouds in one region and extrapolate out and generalize patterns that you can use in your assumptions for other boxes.
And, if there's this temperature and this humidity, how many clouds do I have of what type and so on, right? And there's a lot of variability in those assumptions. And a lot of the art of model building has got to do with how you make those subgrid scale assumptions. So the clouds are really important in the models, and the experts say that the clouds, and in particular the way clouds interact with aerosols, the particles that we're putting up in the atmosphere, are the biggest uncertainty in the models.
How much uncertainty are we talking about here?
Well, one common measure of the models is how much will the temperature go up if we doubled carbon dioxide? And the previous estimates ranged anywhere from 1.5 degrees to 4.5 degrees. And the most recent generation of models, which will inform the next UN assessment report to be issued in July, are even more uncertain than that. Some of them say the temperature would go up as much as 6 degrees, and others say the temperature would go only up by 1.5 degrees if we were to double carbon dioxide from the pre-industrial.
So on the face of it, that doesn't make sense, right? I mean, most people are going to hear that and they're going to say, how can more advanced models give us a wider range of outcomes?
Right. Well, we are trying to understand the response of the system to a less than 1% influence. It's chaotic. it's multi-scale, and we have incomplete observations. So it's not surprising that the science is unsettled.
How much of this is also because we're talking about a complex dynamic system that exhibits feedback? So when you push on one part of the system, when you affect the value of one variable, that then can lead to a series of positive reinforcements that exacerbate that initial movement, causing indirect effects.
Right. Indeed, the feedbacks are really important. They are thought to amplify the direct warming effect of greenhouse gases by a factor of 2 or 3. However, they're not something that we can measure or compute from first principles. We have to see them emerge from the models. Of course, we have some guidance from observations, but that's one of the trickiest things that the models have to get right.
So are methane bombs an example of that? The phenomenon of melting permafrost leading to the decomposition of organic material, releasing methane into the atmosphere, leading to further warming?
Right. So methane is a very potent greenhouse gas. Most of what's emitted is actually from agriculture rather than from fossil fuels, but nevertheless, it's very important. There is a lot of methane tied up in the permafrost and under the ocean, and people are concerned that if the temperature gets warmer, it will start to be released from the permafrost. I can't say we've got much definitive evidence of that right now. It's one of the things that some people think are lurking out there.
When you say there isn't much definitive evidence, what is the uncertainty around that exactly? Because it seems pretty straightforward.
I don't know the precise numbers, but I do not believe that we've seen a great deal of methane outgassing from the Arctic regions, which is where you would expect it to show up.
So we have instrumental readings on that data?
Of course, people are trying to measure the methane coming out of the tundra.
Mm-hmm. Okay, so let's get back to the modeling here a second, because I think this is also a good opportunity for us to differentiate between weather and climate. When we talk about, or when you talk about the chaos that exists in these simulations, this is something that we have firsthand experience with as daily consumers of weather forecasts. As the days pass, it becomes incrementally difficult to forecast the weather with any degree of accuracy. How much of this is similar to how we make projections about the Earth's climate?
Yeah, it's quite different, although many people use the same computer codes to describe climate as they do weather. Let me tell you why they're different. Weather is largely what we call an initial value problem. If you know the state of the atmosphere now, you can pretty well use the basic laws of physics, if your computer model has got a fine enough description, to do a reasonable job of predicting a couple days out. And our ability to predict or forecast, to be more technically correct, has gotten better over the last 50 or 60 years, largely due to finer and more sophisticated computer models, but also better knowledge of the weather today in order to let us forecast what's going to happen tomorrow. Even still, the ability, the accuracy of our forecast, the skill, pretty well gives out after about 10 days or 12 days or so. And that's because the weather system is chaotic. Small changes in what we think the atmosphere is today can lead to large changes in our forecast 10 days out, 12 days out. And this is the famous butterfly effect or chaos that was discovered by Ed Lorenz at MIT in the early 60s.
Is that part of what we mean, or what scientists mean when they talk about tuning the models? Does that relate to starting conditions?
No, that's a different discussion, and we can talk about tuning in a bit. But let me continue on weather and then discuss its difference with climate. The other difference in weather is that the dynamics of the ocean, the changes in the ocean, don't matter at all for the next 10 days or 12 days. The ocean doesn't change. The temperatures of the ocean are fixed during that time, are essentially fixed. And so we don't have to worry about the dynamics of the ocean in forecasting weather. Climate is completely different. Its timescales are decades to centuries over which it changes. In fact, the official definition of climate is a 30-year average. And so on those timescales, We very much need to know about how the ocean is changing. And also on those timescales, the detailed initial conditions hardly matter because they get washed out or forgotten after 10 days or 2 weeks. And so it's a very different kind of problem. And people who say, well, we can predict weather and therefore we should be able to understand climate, they just don't know what they're talking about.
So are you saying that setting initial conditions is a much bigger challenge when thinking about climate? And if that's true, how much of that is because climate is happening on a much bigger scale? I mean, am I thinking about that correctly?
Yeah, the analogy I like to use, which is almost a physical analogy for the weather, is a boiling pot of water. If you try to describe the bubbles in detail, which is like the weather, it's very difficult to do that. And of course, it changes rapidly and it's chaotic and so on. On the other hand, if you want to talk about how the average level of the water will decline as the water evaporates, we can predict that with fair confidence.
In other words, the macro observations are easier to predict than the micro observations.
Yes, except that the macro phenomena we're looking at are small changes that happen over decades.
And we also want to understand how those changes impact the micro phenomena, things like hurricanes,
Absolutely.
Tornadoes, droughts. So that actually leads me to another question. I don't want to derail us because I want to make sure that you can continue explaining what else you wanted to say. But one of the other areas where there are clearly a lot of assumptions baked in here is how changes in temperature will impact ecosystems. And in turn, there's an additional set of assumptions, which is how changes in ecosystems will impact human beings. And that's when we get to questions about, climate refugees, migrations, wars, etc.
Right. Would you like to continue on the models?
Sure, let's continue on the models and we can pick up on that later.
So having, set up your models and the grid and the basic laws of physics and made some decisions about the subgrid scale parameterizations, you're still faced with two other problems. One is, how do I initialize the model? After all, we don't know the detailed state of the atmosphere or the oceans 1,000 years ago. And so what people do is to start up the models sometime very far in the past with no human influences at all and run them for some number of centuries until they come into balance, that the ocean currents on a large scale look right, you get a jet stream, the temperature of the planet's about right, and so on. And then you say, okay, I'll take this arbitrary point in time as the starting point. Let me now start applying human influences, let's say over the last 250 years as we have observed them, and watch how the climate changes. And of course, there is some arbitrariness and importance as to exactly when you choose that starting point. And so what people do is take many different starting points and just average the results together. And of course, the results can differ wildly depending upon how you start them. The last thing that needs to be done is to tune the model. The subgrid parameterizations all have parameters in them. How much does the albedo of the forest change when there's snow on it, for example? Or exactly how much water vapor is transported upward in convection in the warm equator from the sea surface? Things of that sort. And we don't know those numbers. They're adjustable. We can make reasonable guesses, but the precision that we need to understand the climate system with mandates that we fiddle with those numbers in order to get things to look about right. And so there's a good deal of tuning that goes on. In some cases, the parameters need to be set very differently than what we thought they would be. In other cases, the models are tuned to kind of give the results that people expect. And so it is a pretty subtle business that is necessary but not often discussed.
So here's a question I have, because earlier on in our discussion, you said that the last generation models gave us a range of roughly 1.5 to 4.5 degrees of warming in, I assume, the 21st century. Is that right?
No, that's what's called the equilibrium. Namely, if you took the unperturbed planet and you doubled the carbon dioxide, how much would the new temperature be?
Okay.
That's not the warming during the last century.
No, not the last century, projecting forward. These are projections about what would happen over the course of 100 years if you double the warming, or this would just be immediately
That's correct.
if you warm?
Well, they actually do it several different ways, but one way is to just suddenly double the CO2,
okay,
and that's how much the temperature went up.
So in both of those cases, the lower bound is close to or roughly at the maximum threshold that a broad part of the scientific community engaged in this subject have identified as sort of critical. Maybe that number is 2 degrees of warming. I've seen the UN, I think it is, that put it out, or that maybe it was under the Paris Climate Accords, 1.5
the Paris
to 2
Accords
degrees.
started out at 2 degrees, and more recently they've set a goal of keeping the warming due to human influences down to 1.5 degrees.
So now, if we were to agree that 1.5 to 2 degrees, anything above that would be catastrophic, then it seems in some ways much more reasonable to look at these models and say, well, there's a lot of uncertainty, but the uncertainty is on the upside, it's not on the downside. And so the question is, how much do we know about what the effect of 2 or 3 degrees of warming or 4 degrees of warming on the planet would be?
Yeah.
And how in line are people's understandings of what the effects would be versus what the data and the models actually say they would be?
Yeah, that's a really tricky question because you start compounding our uncertainties in future emissions and concentrations, so future human influences. Then that gets fed into what the future climate is going to be and events associated with the climate. And then that compounds into how the ecosystems are going to respond, and then finally how human society is going to respond. And it's extraordinarily murky from what I read. One of the few quantitative predictions is in the models is the net economic impact of warming, both on the US and globally, and even for warming 2 or 3 times the Paris goal.
When you say 2 or 3 times, do you mean 4 to 6 degrees of warming?
Yes, correct. Or let's say up to, 1.5 times 3 is 4.5. Let's say 5 degrees of warming. The net economic impact is 6 or 7% of GDP in 2090, or roughly 100 years from now.
Annual, every year, or in just 1 year, total, absolute impact?
In other words, the economy would be 6% less in 2090 than it would have been otherwise.
Where's that data coming from? Where are those projections coming from?
That's not data, that's projections. And it's the kind of best guess that the economists can make on what the influence of temperature is going to be.
Is this in the actual climate reports?
Absolutely. Absolutely. Both in the U.S. report and in the UN reports. And in the book, I give reference, I actually show the figures. So now let's say 6%, that sounds like a lot, right? If the U.S. economy is $80 trillion a year, which it would be in 2090 if it grows at 2% a year, that sounds like a lot. But it is only 3 years worth of growth in 2090. Namely, our growth in the economy in the U.S., for example, would be delayed by only 2 or 3 years for warming that's much greater than what the Paris Accord aspires to limit us to.
Mm-hmm.
Now, you can disbelieve the economists, all right? On the other hand, that's what the science currently says.
What about ecosystem decline? How much of that is climate related? Like, what is our degree of certainty around that and how it'll be impacted by rising temperatures? Do we have some idea?
Yeah, I have not studied the ecosystem parts of the UN or U.S. government reports in great detail. My impression is the science is, on the standards of physical science certainly, is pretty murky. And again, you have a lot of trouble disentangling natural variability from effects caused by rising temperatures, which may or may not be caused largely by human influences. So very tough, I think, for me to give an informed opinion about that.
So I want to ask you one more question before we move it to the overtime, Professor, because in the book, among some of those projections that we discussed, like economic costs, you also discuss the effect on agricultural yields and food supply. This is a huge concern for people, and one of the reasons why we have projections around climate refugees and migration. For example, there's a very popular book on this subject whose author was on Joe Rogan a couple of years ago. I heard the episode recently, and he cited a number of 1 billion climate refugees by the end of the century. A lot of that has to do with the expectations that warming will lead to significant crop failures, lower yields, and starvation for hundreds of millions or over 1 billion people. So what do we know about the impact that rising temperature and climate change, based on projections that have been made, what effect that would have on yields of crops and our capacity to carry the population of the earth by providing enough food to feed them?
Yeah. So, of course, it's a murky business like many of these impact things are. Nevertheless, the UN in its so-called Working Group 2, or its special report on climate change and the land, certainly discusses what has been and what might be in the future. Again, let's start with what has been. First, if you look since 1960, the yields and the production of food has just gone through the roof. And the yields, for example, of corn in the U.S., corn globally, rice, wheat, they've all gone up strongly, due largely to technology, to agricultural practices, and to breeding of the crops. Now, what the report says is that if the temperature hadn't gone up, well, the yields would have gone down by a few percent. Rather than having gone up by 100%, they would have gone up by, let's say, 93% or something. As a scientist, I would say, how do you know that? That's a counterfactual, as we say in the business, and it's extraordinarily difficult to opine with that with any degree of credibility. You've got to know how things would have happened if the climate hadn't changed. For example, how would agricultural practices have changed and so on. But the bottom line for me in that is that the projected impacts or the predicted impacts were small. Now we can talk about going out in the future, and they don't say much. It's very hard to find quantitative statements. One of the few quantitative statements that they do say is that we could see an increase in food prices by 2050 under moderate scenarios, an average of 7% increase in the price, but anywhere between 1 and 23% in grain prices. And to me, that's a
From their current levels, inflation adjusted?
Well, they don't say probably what they would have been otherwise. But to me, that's a ridiculous statement, because the price depends on the balance of supply and demand, which are two big numbers, and the difference is what determine the price. But even if you believe the 23% impact, when you look historically at how grain prices have fluctuated over the last century, it's by much more than 23%. So I think, like many things associated with climate impacts, small and in the noise is what one can conclude from that. And again, not Steve talking, this is what's in the reports, and in the book, of course, I give the references and the graphs and so on.
So something I actually forgot to ask you, and I want to ask it before we move into the overtime, deals with backtesting. How effective are these models across the board? And how good are they at predicting warming in the past, ex post, using historical data?
Yeah. So hindcasting, as it's called in the business, is to take the state of the climate in some point in the past and then run it forward under what we think are the human influences and see whether we match the observations that we've had from that point in the past up to the current. And for the global temperature record, on average, it produces about the amount of warming that we have seen, although there's some amount of tuning that goes into that in order to get that result. But the detailed behavior over, let's say, several decade periods is quite wrong. It misses the strong warming at the beginning of the 20th century. It doesn't do a great job on the slight cooling. And of course, it does pretty well over the last 30 or 40 years, in part because, as some of the experts will admit, there's some amount of tuning that goes on in order to get that. When you start to look beyond the global temperature at things on a regional scale, for example, rain in California, temperature extremes, they get pretty bad. And I would say the uncertainties are large enough to be effectively useless in trying to understand how we're going to respond in the future.
But you would say that they're pretty effective in predicting future warming?
Global temperature. Well, we talked about the uncertainties in the future warming. Just because you've gotten the last 40 years right doesn't mean you're going to get the next 100 years right. And one of the big uncertainties is this balance between sensitivity to greenhouse gas warming and aerosol cooling. And the other big uncertainty is an inability to reproduce these multi-decadal natural oscillations of the climate system.
So I'm going to move the second half of our conversation into the overtime, Professor. I want to delve deeper into some of these extreme weather phenomena because I think there are a lot of interesting cases in the book. We haven't had a chance to discuss sea levels. I know that's a really big one for people. We touched on hurricanes early on, and we touched on forest fires. I think droughts are also relevant. I don't know to what degree we already discussed those. I also want to explore the incentives that might account for some of the diverging narratives that exist. You know, who are the stakeholders? Why has this view become such a prevalent view? And I think that also relates to morals and values and how we think about costs, because there are costs to making this a global priority if we can manage to do that. There are also questions about whether that's even possible and what are the most effective ways to allocate our time, because I think that's very important. I think a lot of times when this is discussed, people don't take that into account, and I think that that's unrealistic. I also want to ask you about geoengineering, because I assume some of that relates to your work when you were at BP. You probably learned a lot about where the technology was at that time, and I assume you've stayed abreast. You discuss solar radiation management in the book. I want to ask you about that. That has to do a lot with, I suppose, you would call it reflectivity of the Earth's atmosphere, the albedo of the Earth.
Right.
And carbon dioxide removal, which is something carbon capture, so to speak, that people are pretty familiar with. I want to delve into those because I really want to get specific on what the costs are, how realistic these technologies are. There are reports recently that Bill Gates is an investor in one particular company out of Boston where they're focused on actually trying to increase the Earth's albedo. So I'm curious to know what you think the costs would be to actually implement something like that, how realistic, and then what the risks are. And of course, we're going to be discussing alternative sources of energy, including the viability of nuclear, because I want to know what your thoughts are on that and if we can really reach any of these ambitious emission targets without building more nuclear power plants. For anyone who is new to the program, Hidden Forces is listener supported. We don't accept advertisers or commercial sponsors. The entire show is funded from top to bottom by listeners like you. If you want access to the second part of my conversation with Steven, as well as to the transcripts and rundowns to this episode and every other episode we've ever done, head over to hiddenforces.io to check out our episode library or subscribe directly through our Patreon page at patreon.com/hiddenforces. There's also a link in the summary page to this episode with instructions on how to connect the overtime feed to your phone so that you can listen to these extra discussions just like you listen to the regular podcast. Steven, stick around. We're going to move the second half of our conversation into the subscriber overtime.
That's great. Not going anywhere.
Today's episode of Hidden Forces was recorded in New York City. For more information about this week's episode, or if you want easy access to related programming, visit our website at hiddenforces.io and subscribe to our free email list. If you want access to overtime segments, episode transcripts, and show rundowns full of links and detailed information related to each and every episode, check out our premium subscription, available through the Hidden Forces website or through our Patreon page at patreon.com/hiddenforces. Today's episode was produced by me and edited by Stylianos Nicolaou. For more episodes, you can check out our website at hiddenforces.io. Join the conversation at Facebook, Twitter, and Instagram at Hidden Forces Pod, or send me an email at dk@hiddenforces.io. As always, thanks for listening. We'll see you next week.